Hello everyone, welcome to Chem Analysis. In today's question answer discussion series video, I will solve previous year CSIR-NET December 2017 inorganic questions, and the candidates who are preparing for CSIR-NET and GATE examination along with other competitive chemistry examination, this series is going to be very helpful for you, since when you see a detailed solution of a question, then the related thing corresponding to that topic will become clear for you. So don't miss any video of this series, and without any further delay, let's start it. So the first question, we can see that it is given in trigonal prismatic ligand field, the most stabilized d orbital we have to identify. Now if we see the structure or geometry of a trigonal prism conformation, then we can see that the metal ligand bonds, these red are ligand and the center atom is the metal, and we can see that the metal ligand bonds are oriented along xz and yz axis. If we consider this axis as x, this as y, and this one as z, we can see that this metal, all the metal ligand bonds are oriented in the xz plane or yz plane. There is no ligand in the xy plane or along z axis. Thus we can say that the dxz and dyz metal orbital will face electronic repulsion with the ligand orbital. So the energy of dxz and dyz will be highest for the metal. Now we can see that there is no ligand along xy plane or along z axis. So after this 2d orbital, there will come into play dxy, dx square minus y square, and dz square orbital, and dxy and dx square minus y square will be similar in energy since they are oriented along the xy plane. Now if we see the d orbital shape of dxy and dx square minus y square, then we can see that in dxy there will be 4 lobe, and in dx square minus y square orbital there will be also 4 lobe. But in the dz square orbital there is mainly 2 lobe, and there is a electron cloud around the center. So electronic repulsion with the 2 lobes of dz square orbital will be less in comparison to the electronic repulsion of the ligand with the 4d orbital of dxy and dx square minus y square orbital. Therefore after dxz and dyz there will come dxy and dx square minus y square, and after that the lowest energy orbital will be dz square. Is it clear? So we can see, since the energy of dz square orbital is lowest, so more stable, here it is asked that more stabilized orbital, so dz square orbital will be more stable. So we can see that option number 1 is the correct answer. So next, see another question. Here it is given that the IR spectrum of cobalt CO4H shows bands at this 4 value in centimeter inverse. We have to identify the value of frequency of cobalt deuterium bond. Now from the given 4 value, we can say that in generally if there is free carbonyl, then the stretching frequency of free carbonyl is near about 2143 centimeter inverse. Now in the complex, in the metal complex, there will be a decreasing of the carbonyl stretching frequency. So we can see here from this value we can say that this 2043, 2062 and 2121, this 3 value corresponds to this 4 carbonyl unit. Now to know how these 3 bands is coming for the 4 carbonyl units in this metal carbonyl complex, you can watch my previous video where I have discussed about how to calculate the number of stretching bands for a metal carbonyl complex, and there I have discussed thoroughly about how to calculate carbonyl stretching bands for a metal carbonyl. And generally, if you know the geometry and point group of a metal carbonyl, then you can easily identify the number of stretching bands for carbonyl units. So here we can say that this 1934 centimeter inverse, this frequency is for cobalt hydrogen bonds. Okay. Now if we write the stretching frequency equation, then it is like that: 1 by 2 pi c root over k by mu. Here k is the force constant of cobalt hydrogen bond, mu is the reduced mass of cobalt hydrogen bond, and c is the velocity of light, and pi you know. And if we write the stretching frequency equation for cobalt deuterium bond, then we can write it like this one. Here mu is for cobalt hydrogen, and here mu is for cobalt deuterium, and force constant is for cobalt hydrogen, here is cobalt deuterium. Now the force constant for cobalt hydrogen bond and cobalt deuterium bond is not so much different. The cobalt deuterium bond is stronger enough than that of cobalt hydrogen bond, but the difference is not so much. So we can consider the force constant for cobalt hydrogen and cobalt deuterium bond is quite similar. Now we have to calculate the mu for cobalt hydrogen bond as well as mu for cobalt deuterium bond. Then we can calculate the value of mu carbon deuterium bond. So if we write the equation for reduced mass, then it will be atomic mass of cobalt into atomic mass of hydrogen divided by atomic mass of cobalt and plus atomic mass of hydrogen. Now the atomic mass of cobalt is near about 59, and for hydrogen it is 1, and in the denominator it will be like this. So we can write it 59 by 60. Now similarly for cobalt deuterium bond, it will be, here will be mass of cobalt 59, and here will be mass of deuterium, it is 2, and in the denominator there will be 59 plus 2. So we can see here that 59 divided by 61 into 2, and this is double of, near about double of cobalt hydrogen reduced mass. So putting this value of cobalt deuterium reduced mass in this equation, then we can get the value like this. So let first erase the above thing. So we can see here if we put in place of force constant of cobalt deuterium is equal to force constant of cobalt hydrogen, since both are quite similar, and in place of cobalt deuterium we are writing 2 into mu of cobalt hydrogen. Now the value of this term is given here, that is 1934 centimeter inverse. So here if we solve it, it will be like this into mu of COH. Is it okay? So if we put the value of this term, then it will be 1934 centimeter inverse, and if we calculate the value, it will be near about 3070 centimeter inverse. And in the given option you can see that the nearer value is 1396 centimeter inverse, and this slightly higher value is due to consideration of a real force constant of cobalt deuterium bond, since we have considered here that cobalt deuterium bond force constant is similar to cobalt hydrogen, but in generally it will be slightly higher than this cobalt hydrogen force constant. So there will be some additional factor multiplication with this 1370 centimeter inverse, and in reality the result will be 3096 centimeter inverse. Is it clear? So option number 2 will be the correct answer. So let's see another question. Here we have to identify, it is a very simple question, it is from valence bond theory. We have to identify the pyramidal shape of the given species. So for the first one, we can see that here is chlorine central atom, and for chlorine there is 7 electron and there is 3 oxygen. So each oxygen will contribute 2 electron. So from 3 oxygen there will come 6 electron, and there is one anionic charge, so there will be another addition of 1 electron. So in total we can see that there is 14 electron, that means 7 electron pair, and among the 7 electron pair there will be 3 pi bond with the chlorine and oxygen atom. Since oxygen is providing 2 electrons, so 1 electron will form a sigma bond and another electron will form a pi bond with chlorine atom. So there will be 3, since there is 3 oxygen atom, there will be 3 pi bond, and pi bond is under consideration for hybridization. And there is 4 electron pair, and among these 4 electron pair 3 sigma and 1 is lone pair. So hybridization of ClO3 minus is sp3, and sp3 with 1 lone pair electron, so it will be pyramidal. So this one is pyramidal. And for the XeO3, it is for ClO3 minus. For XeO3, xenon is central atom and it will contribute 8 electron, and 3 oxygen will contribute 6 electron. So 14 electron, that means 7 electron pair, and among these 3 will be pi bond, and 4 electron pair. Among this 4 electron pair, 3 will be sigma bond and 1 will be lone pair, since there is 3 oxygen atom. So it is also sp3 hybridized and pyramidal. So it is also pyramidal. And for the last case, that is SO3, sulfur will contribute 6 electron and 3 oxygen will also contribute 6 electron, that is total 12 electron, that is 6 electron pair. And among these 3 electron pair there will be 3 pi bond, and it is not considered in hybridization, and another 3 electron pair will form 3 sigma bond. Since there is 3 sigma bond, it is not sp3 hybridized or not pyramidal shape. It will be sp2 hybridized, that is trigonal planar. So we can see that 1 and 2 is the pyramidal geometry, so option number 1 is the correct answer. Here we have to identify the geometry of these two species, that is SnF3 and XeF2O2. And in SnF3, the central atom is not nitrogen, the central atom is sulfur. So for sulfur will contribute 6 electron, and there will be 3 electron from 3 fluorine atom, it is from fluorine atom, and the nitrogen will donate 3 electron to sulfur and will form 3 bond. This 3 electron from nitrogen, that means total of 12 electron, that is 6 electron pair. And among the 6 electron pair there will be 2 pi bond between sulfur and nitrogen, since nitrogen will form 3 bond providing 3 electron, and among them 1 will be sigma bond and 2 will be pi bond. So here is 2 pi bond, and the remaining 4 electron pair will contribute 4 sigma bond. So the hybridization of central sulfur atom in SnF3 is sp3, and since hybridization is sp3, that means the geometry is tetrahedral. Since there is no lone pair electron and there is 4 sigma bond for sp3 hybridization, so tetrahedral. In the next case, XeO2F2, central atom xenon will contribute 8 electron, 2 fluorine atom contribute 2 electron, and 2 oxygen atom will contribute total 4 electron, since each oxygen is contributing 2 electron. So in total there will be 14 electron and 7 electron pair, and among these there will be 2 pi bond between oxygen and xenon. so 2 pi bond, and among the remaining 5 electron pair there will be 4 sigma bond and 1 lone pair. And since 4 sigma bond and 1 lone pair, that means hybridization will be sp3d, that is trigonal bipyramidal. Okay, so we can see that option number 4 is the correct answer. Now next question, it is a very important question. We have to identify the first ionization energy, lowest first ionization energy from this given species. Now before going to solve these questions, let know some important points regarding ionization energy. Ionization energy is the minimum amount of energy required to eliminate an electron from the valence shell of an atom. With increasing electronegativity, that means if we go along a period from left to right, electronegativity of the atom increases and size of the atom decreases, effective nuclear charge increases, and the general trend is in a period from going left to right is ionization energy for the element increases. That means with increasing electronegativity, ionization energy increases, decreasing size, ionization energy increases, and increasing effective nuclear charge. Since with increasing effective nuclear charge, the valence electron feel strong interaction with the nucleus, so energy required to eliminate an electron from the valence shell increases, so ionization energy increases. And similar is the case for electronegativity. And similarly, in a group from going top to bottom, in generally electronegativity decreases and size increases, and with this factor we can conclude that in general trends ionization energy decreases. Now among these factors there is one important factor that sometimes play the real game, and that is the electronic configuration. The effect of this electronic configuration will come into play when we go in a period from left to right. That is, if we consider two elements, when we go from left to right from this 1 to 2, we can think that ionization energy for 2 will be higher than that of ionization energy of 1. Now if there is observed that the element 1 containing in any half filled or full filled electronic configuration, then it is observed that the ionization energy of the first element is higher than that of second element, since in that case electron removal from a half filled or full filled, that is more stable electronic configuration, is quite difficult than that of the second element. And for that cases the order for ionization energy get reversed, and it is applicable for the neighboring element along a period. And here in the given 4 element we can see that phosphorus is the element of third period, and electronic configuration, valence shell electronic configuration is 3s2 3p3, and below this element there is arsenic, whose electronic is element of fourth period, and electronic configuration is 4s2 4p3. And similarly for selenium, it is selenium come after arsenic in the same period, that is arsenic after selenium, and its electronic configuration is 4s2 4p4, and after selenium there came bromine, whose electronic configuration is 4s2 4p5. Okay, now if we compare the ionization energy for these 4 elements, since phosphorus is remaining one period upper and its size is lower than that of these 3 elements, since these are element of later period, so the size of these elements will be higher than that of phosphorus, so phosphorus will show highest ionization energy, or phosphorus will be highest than that of other 3 elements. Now among arsenic, selenium and bromine, as we go from left to right, then the size decreases, electronegativity increases, and effective nuclear charge also increases, so we can consider that ionization energy will increase. Okay, now if we see the electronic configuration of arsenic and selenium, we can see that arsenic, that is before selenium, is containing half filled electronic configuration in the p orbital and fulfilled in the 4s orbital. Since electron will eliminate or electron will liberate from the 4p orbital and it is containing more stable half filled electronic configuration than that of 4p4 for selenium, so electron removal from this half filled electronic configuration will be difficult than that of selenium. So we can say that selenium will have less ionization energy than that of arsenic. And when you go from selenium to bromine, there is no such stabilizing factor that half filled or full filled. And you can think another way that 4p4, after releasing one electron, it will get half filled 4p3 electronic configuration, but bromine will not get such electronic configuration. So selenium can easily remove one electron from the p orbital. So we can say finally that the selenium will show the lowest first ionization energy. Since here is considering the first ionization energy, so we have to consider the liberation of one electron only. That means selenium will show the lowest ionization energy among these four elements. Is it clear? If no, then let me know in the comment section. Now it is a question from coordination chemistry, and we have to identify the order of magnetic moment, spin only magnetic moments for this four given complex. Now the expression of spin only value is 2 into s plus 1 Bohr magneton. Higher the number of unpaired electron, that means higher the spin, higher will be the mu spin only value. So from the given four option, in TiF6 3 minus, titanium is in plus 3 oxidation state and electronic configuration is 3d1, and chromium F6 3 minus, that is here also chromium is in plus 3 oxidation state and electronic configuration is 3d3. Here will be argon. I have not written the inner shell electronic configuration. And for the manganese 3 plus, there will be argon 3d4, and all the complexes will be high spin since fluorine is a weak field ligand. And in the last case, that is cobalt 3 plus, is electronic configuration will be argon 3d6. Now the number of unpaired electron for this TiF6 3 minus is 1, and for chromium F6 3 minus is 3. For manganese F6 3 minus, the number of unpaired electron is 4, and in cobalt F6 3 minus, if we draw the electronic arrangement, that is, since it is high spin complex, first there will be filling of each unpaired electron in each orbital, then since there is 6 electrons, so the remaining 1 electron will pair one unpaired electron. So we can see that there is 4 unpaired electron, and manganese complex also has 4 unpaired electrons. So magnetic moment of these two complex, that is C and D, will be similar, and these two species C and D will have higher spin only magnetic moment than that of B and A, and after C and D it will come B, since it contains 3 unpaired electron, and the last there will be A, since it contains 1 unpaired electron. So this is the correct order for the spin only values, and we can see that option number D is the correct answer. So these are the things for this discussion. I will later also upload the 4 marker questions of inorganic chemistry of December 2017 CSIR-NET questions. So thank you for watching, and if you are new in this channel, then don't forget to subscribe my channel Chem Analysis to get such really interesting videos in future. Thank you once again.